Okay, good morning, everybody. It's my pleasure to greet you here in Boulder, Santa Green. This workshop has been in planning for almost 2 years, and we kept pushing it, hoping for the end of the pandemic. And it's almost over. We can see you in person, so that's great. We do have about 50 people online that joining us today. So this is a workshop organized by US CLIVAR. Organizing committee include myself, Cecilia Rousseau, Tom Lanier, Dick D, Ron Gelaro, Patrick Heimbach, Ayla Simpson, and Laura Slavinsky. The focus of this workshop was on a vision for the future of US reanalysis effort. So what's important to note here is that we're not talking about a single reanalysis here. We're talking about how all of our efforts work together. And the reason it's focused on US is because as part of CLIVAR, we have connection to program managers in US, and we'll be having a conversation with them following this workshop. But I think that scientifically, this will be a very interesting conversation for our colleagues outside of US, and in fact, we have a lot of speakers and online attendance from Europe. Okay, so outcomes of this workshop. We would like to develop a 10-year vision for reanalysis that is consistent across Earth system components. By consistent, one of the jobs we need to do is actually define what consistent means. We try to avoid using the word coupled because that's very technically specific. So we'll be having a lot of discussion about what consistent means during this workshop.
Gluten is now an enemy.
What?
Not sure. Everyone is muted online.
Okay. So there will be 3 components of the workshop: scientific goals, technological advancements, and tactical operations. For scientific goals, we want to talk about the next generation of reanalysis from atmospheric, oceanographic, and cryospheric perspective. We want to find technological opportunities to explore technological advancements in Earth system models, data simulation, observations, computational infrastructure. We want to set priorities and identify opportunities for tighter collaboration between US institutions and international community. Next slide, please. So this workshop has been ongoing since January when we had a series of webinars. And I'll give a quick overview of these talks. I could not possibly give justice to these talks in 5 minutes. So I'll talk about the broad themes that inspired the conversations following from these talks. So next slide, please. So Laura Slavinsky has introduced this series of webinars, and the first webinar was from Tom Hamill from NOAA PSL, now from IBM, and from Gil Liscano from Climate Scale. And essentially, their talks presented this idea that's very similar to this idea of digital twins that is circulated in the community. And you can formulate it as following. So you start with a global reanalysis and reforecast. And as a part of it, there are multiple links to users through either typical NWP post-processing. So the first figure on the left here shows improved precipitation skills from post-processed and non-post-processed analysis. The middle figure here shows a very commercial-driven application where you want to take NWP products and actually advance them up the value chain and produce products that can be used by wind energy or solar energy producers in their planning and execution cycles. And the last figure here is from one of the new growing array of neural network papers where they take reanalysis and they take some neural network predictors for it. And that's a really large growing new user base for reanalysis that could really benefit from more rapid refresh of reanalysis products. Next slide, please. We also had 2 talks on advanced scientific uses of reanalysis from Karina von Schuckmann at Mercator Ocean on heat sequestration in the ocean, and from Clara Orbe from NASA Goddard on stratospheric-tropospheric interactions. There were excellent talk, each on their own subject area, and it's impossible to summarize it. But maybe what's important to take from them is that there are very detailed scientific analysis that the scientific community is developing that support a lot of highly impactful applications like IPCC assessment. There'll be this ocean heat contact from APCAR6, or age of air anomalies that can fit into climate intervention studies. So the very fine-tuned analysis that take years to develop. And we have an opportunity to close this loop sooner with the scientific community. That it's not we produce a reanalysis and they spend 5 years analyzing them and then they publish the paper. And by the time we read the paper, we already produce the next reanalysis. So the decisions has been made how it's going to be done. So the next set of talks was from observation community. We have one talk by Arnaldo de Silva, which was forward-looking about the future observing systems. And we had 2 talks from Lyndon Ashcroft and Elizabeth Kent about observation recovery. And I'll have shown this picture about crew temp, which is surface temperature data set that usually is not used in the reanalysis, but it's used to evaluate reanalysis. And it shows how the coverage of surface temperature changes through time, which is not surprising. Different colors show how the data set itself evolves through reprocessing efforts. And the take-home message was that if you look at the observational record and its continuity, you can start really seeing different periods of the record. There's a sparse instrumental record from middle 19th century up to past World War II. There is a conventional record when we have from 1950s to 1979, where we have extensive coverage with conventional observations, but the satellite record is non-existent. We have 1979 to end of the century, where we have early satellite record focused on 2D images of Earth. It's one way to think about it. We have modern satellite record and Argo period starting from 2000s, where we start having profiling satellite measurements and Argos that can profile the ocean. And we have this postmodern satellite record, all these satellite sensors that will start observing atmosphere as a continuum from precipitation, clouds, to aerosols, to vertical motion. So when we think about our consistent reanalysis across different components of the system, composition, CO2, cryosphere, I think it will be good for us to contextualize our discussion in terms of observational data available to support this reanalysis. Next slide, please. And finally, we had one talk from industry. It was from Tom Augsburger from Microsoft. And he was arguing that we're really moving to a different way we're interacting with the data. So if on the left is our traditional way of interacting with the data, we have ERA 5 data sets stored in Europe, MIRA 2 stored somewhere in the US, and Landsat imagery stored in another place, and we're downloading them locally and try to write our algorithms and process them on our local machines. What the industry is envisioning, and we can see it echoed in European cloud initiatives, where all the data is collocated. So there'll be a single warehouse, data warehouse, where we have ERA 5, MIRA, future versions of ERA, MIRA, satellite data, all collocated in one data warehouse. And we'll be writing software that will be operating out of the same facility. And the only things that we download will be through the results. And these downloads will be much smaller than the original data sets. Next slide, please. So that was a summary of the talks we had so far, and hopefully they kind of give you an outline of the type of discussions we will hope to have through this 2.5 days. I want to mention a couple of words about diversity and inclusion. There are various aspects to diversity. The first one is gender. That's the easiest one to measure, and that's we spend a lot of time thinking about it because it's easy to measure. In terms of participants, we have about 1/3 female versus 2/3 male. And we know the general population doesn't split that way. It's more like 50-50. We spent some effort trying to understand what the natural breakdown of our community is. And it indeed is 1/3 to 2/3. When we looked at gender participation of speakers, we have closer to 50-50. I think it's very important to acknowledge that the first time we put the program together, it was 9% female and 91% male. And it was despite the fact that we had a very diverse scientific steering committee. And it was essentially a manifestation of implicit bias, because every time we thought about the topic, we thought about a distinguished male speaker to lead it. So that was not acceptable to us, and we went through a consistent effort to think what it would take to improve our representation. And the way we went about it, if we thought that a certain topic can be covered as well by female speakers as male speakers, we gave preference to female speakers. And every time a male speaker canceled, we tried to find a female replacement. And I think our efforts paid off. By region, most of the participants are from US. In terms of speakers, we have a more even distribution between Europe and US, and I think it's a recognition of the effort done through Copernicus and the European Center to achieve excellence in reanalysis. In terms of race, we have about 60% white or Caucasian and 30% Asian, and the rest of the races are very poorly represented. Next slide, please. Jenny, do you want to say a couple of words about logistics?
Yeah, so we do have some people online. You'll notice in the room there are 3 microphones. So if you have any questions after a speaker's talk or during the discussion, please line up behind one of these microphones so that the online folks can see or can hear you. But in addition, they can see you. You'll notice there are some cameras up on the walls and one on this back wall. Those will zoom in on the speakers. When you do talk into the microphone, I'm a bad example of this actually. Please say your name and your affiliation. So I should have started out with Jenny Zhu, US CLIVAR. I do have an announcement. So that way the online folks know who's speaking. Back to you, Sergey.
Okay, next slide, please. So day 1 goals is a 10-year vision for science of reanalysis. We want to elucidate how science and applications, including numerical weather prediction, can drive the need for consistent reanalysis. We want to identify model components and the level of coupling that is feasible to achieve within the next decade. And we want to catalog observation data available to support this consistent climate reanalysis and identify the needs for any observational rescue or future observing systems. Can you advance the next slide? Okay, go back, that went too far. So I think with that, I have 3 minutes. Are there any questions?
We'll move on to our next speaker is Lesley Ott from NASA Goddard, talking about carbon cycle.
Lesley, I'll give you a 5-minute warning at the 10-minute mark. We'll try to save some time for Q&A.
Awesome, thank you. Okay, well, thanks again for the invite. Thanks for having me. Today I'm going to be talking about carbon cycle reanalysis. Some of the progress, the baby steps that have been made to getting a better representation of carbon cycle into the next generation reanalyses, but also many challenges that we face that I'm hoping we can try to find some strategies to address. And, you know, just to give you an overview, it's very simple to talk about where carbon cycle is in the previous reanalyses and things we've done in our office in GMAO Lake Mare 2, which is non-existent. We don't have that. So we're talking about a really exciting development, being able to add this new cycle in addition to the water and energy cycles that we've been tracking for so long, carbon. But of course, that takes a whole lot of people, it adds a whole lot of complexity, and that's what we're going to be talking about today. And I just want to acknowledge the contributions of all the co-authors who, you know, in part we're talking about accomplishments, but really also highlighting many of the challenges that they're hoping we can help them address. So I want to start with the top level motivation of why you should care about this, because I think by the end of the talk, you're going to think, why even bother? This is really, really hard. But I want to underscore how important this use of reanalysis is. So the carbon cycle, the way that carbon moves between deep reservoirs in the earth to the surface, through the atmosphere, through the ocean, and how all of those things are connected. That's what governs the concentration of carbon dioxide in the atmosphere, the most important greenhouse gas that affects climate change. Now you see this budget-based analysis, which is on the right hand of the screen from the Global Carbon Project. The top plot is showing you the emissions, the carbon that we're adding to the atmosphere. And the bottom plot of that is what's really interesting, is showing where that carbon is ending up. So about half of the carbon that we're emitting to the atmosphere from fossil fuel combustion and land use remains in the atmosphere, contributing to climate change. But the other 50% is being absorbed by the plants on land, by our oceans. That's really a critical resource in reducing the rate of climate change. The problem is we don't necessarily understand those processes on the land and ocean very well. That means we don't know with a lot of confidence whether they're going to continue over the next century. And so just to underscore why this is important, not only is this an interesting scientific problem, this is a policy question, right? We're moving in terms of governments around the world from this place of scientific understanding to action, trying to actually reduce climate change and make decisions based on the science that many people in this room are doing. So that's wonderful. It's also a little terrifying. The right-hand plot is showing you just the representation of global carbon cycle in both the atmosphere, both the land and the ocean. For CMIP6 remains one of the largest sources of uncertainty in the rate of climate change over the coming century. And one thing that's somewhat disappointing, not a lot of reduction of uncertainty from CMIP5 to CMIP6. So we know that this is still a barrier to being able to project how climate is going to evolve over the next century. That makes it hard for people to make good decisions to reduce the effects of climate change on our behalf. So reanalysis of carbon cycle processes, this is the critical underpinning that people need to understand the baseline of how things are changing, to be able to train climate projection models so that we can have better information. So even though the next slides are going to be about many, many things that are going wrong, just keep in mind why we're doing this and how incredibly important this is, not just for science, but also for applications and for policy objectives. Let's see. Okay. So this is a nice schematic of the carbon cycle. You can see all of the different components, the arrows of how carbon is flowing. This is how we would like to understand the carbon cycle, is this big holistic picture. This is really kind of where we are right now, though, is that we are studying all of our little spheres of vegetation side of the carbon cycle with its independent model, atmospheric side, ocean side. In some cases, we're aiming for consistency and forcing, but these things are certainly far away from being consistent, very far away from being coupled. So I'm going to take you through in the next slides just an example of the kind of work that's being done, some of the observations that we have to work on, but then lists from the colleagues that you saw on that first slide of what do we think are the big barriers to making progress and how can we try to address them. So first, let's start with the atmosphere, right? The main thing that's driving climate change. And I want to first call out the atmospheric observing system. So for decades now, we've had in situ CO2 observations. Those started at Scripps. They're now made at NOAA in Boulder, just, I don't know, not quite down the street, but not too far away. Those are still the gold standard in terms of greenhouse gas measurements, very high quality, but unfortunately very sparse. We only have those data maybe at a few dozen sites, and as you go back in time, that number becomes even fewer. So the advent of high quality CO2 observations from satellite, most notably in the GOSAT and OCO era, beginning in 2009, was a real game changer in terms of giving us a more complete global picture. And I'll just note really quickly, when I'm making these tables, this isn't exhaustive. There are also some measurements of greenhouse gases from thermal instruments like AIRS and EASI. Those are mainly sensitive to the upper troposphere and stratosphere. So really a lot of the work that's going on in atmospheric carbon analysis is coming in the context of the GOSAT and OCO satellites. Those are measuring the dry air column average mole fraction of CO2. So that's the full column integrated amount. And I don't know if you're seeing this super well. It didn't translate very well. But the plot, if we look at the work that's been done, this is from our office. If you look at the left panel, this is actually showing you 16 days of accumulated cloud screened OCO data. And if you could see it, you can probably still note it's kind of a gappy data set. The OCO swath is pretty thin. It's about 10 kilometers wide. It's a 16-day revisit time. And we also can't make measurements from OCO in the presence of clouds or thick aerosols. That means we have a lot of gaps in key places like the Amazon. So some of the work we've been doing is to assimilate those retrievals into our constituent assimilation system. This is the same system that's been used to assimilate ozone in things like Maritu, if you're familiar with that, to create a gap-filled map. So that's what you see in that second panel. And from that, we can actually do interesting science just on its own of having a more complete picture. This is the plot, third from the left, is showing you the XCO2 anomaly during COVID. So this is actually using those concentration data to get at a change related to human emissions, being able to track that over time. And we're still using this data set in interactive dashboards from NASA to be able to track changes in the environment using satellite data sets and also being distributed through the JESDISC as an OCO L3 product. So this is in relatively good shape. This is going to go into the R21C reanalysis that Rolf mentioned. So this is something that we're ready to do relatively near term with the atmospheric assimilation. And now I want to go to some things that are challenges / opportunities. As we go through this, a lot of them are really more problems than opportunities, but an opportunity, there's always an opportunity to solve a problem if you don't want to be depressing, right? This one is actually kind of an opportunity for us. I want to make this point. This is a chart, and you don't have to be able to read all the text. That's not the point. This is a table just trying to show the satellites observing greenhouse gases, and it starts in 2021. Sorry, this got a little blurry in the conversion. This starts in 2021 and goes forward over the next decade. You can see kind of the point we are making with OCO and GOSAT. Right now, we've always, with greenhouse gases, with carbon dioxide, we've been living in a data sparse world where we didn't have that much information. Over the next few years, that's going to change. We might have as many as, a half dozen, maybe even more satellites if we can get something out of some of the commercial small sats that are coming out. That's going to be a big challenge for this community. That means big data volumes, being able to have to worry quite a bit about intercalibration between satellites. So this is a challenge that communities like the NWP community have faced for a long time. It's fairly new for the carbon cycle community. So we're going to get hit with this wave of data that I think some of us are prepared for and many of us not quite. I'll also note that, for when we talk about atmospheric CO2, we're assimilating retrievals. We're not assimilating radiances. We're not able to do that right now. That also, in combination with that first point of being able to not just assimilate a lot of, raw data, we're going to have to deal with different people's retrieval algorithms, inconsistencies there. That also adds latency. It puts some barriers on how fast we can turn things around, because right now we're waiting 1 to 2 months for OCO data. That limits how fast we can turn around those analyses. This data estimation methods that I showed, and also some of the inverse methods that I haven't highlighted but do exist, are mainly using atmospheric carbon dioxide measurements to estimate net flux, but it's still challenging to feed that back to a process level understanding of land and ocean. That's what we really need to understand, not just what is the net flux, but how does that constrain processes in some of these models? That's what we need to do to get to better predictions. Limited spatial coverage we also talked about, and the fact that we have a total column measurement from something like OCO2, that gives us limited vertical information. That means we're very sensitive to errors in model transport that can influence the results, particularly when we're trying to estimate surface flux.
5 minutes.
So for the ocean, we're also in pretty good shape in terms of having a lot of mature capabilities. This is work that's done by Cécile Rousseau. And I want to highlight, this is ongoing in our office, the NASA Ocean Biogeochemical Model couples an OGCM with the Ocean Atmosphere Radiative Transfer Model, OASIM, to be able to assimilate ocean color data. The top panels are applying this model in different ways, showing that we can get a realistic characterization of ocean atmosphere flux. And the bottom is using the system and high quality intercalibrated ocean color data sets to look at the trends in ocean color in primary production, and actually to be able to track that back to the processes that are driving changes in ocean productivity. In this case, is changes in the mixed layer depth. But as with all the other things, there's a lot that we need to do in terms of oceanic carbon. Cecile actually chimed in on this in terms of some of the logistical barriers that we face. We mentioned that the ocean color intercalibration it's very, very challenging. That's what the right-hand panel is showing, just the sensitivity of reprocessing of the MODIS data to correct for drift in the blue channels, and how that changes the whole trajectory and interpretation of the ocean color time series. There's also lots of uncertainty in things that we can't see very well. Large uncertainty on the export of carbon from surface to deep oceans. Riverine transport, as Rolf was mentioning, this is a challenge for just the hydrology aspects. We don't have carbon in those systems, and that's a big barrier in terms of being able to connect all of these systems in terms of consistency. The riverine transport, the lateral transport, it's a big deal for us. And also sparse observations in key areas like the Southern Ocean, where we know we're expecting big changes related to climate change. So Rolf has done a good job introducing some of the challenges and status of vegetation assimilation on land, but I do want to highlight a couple things. First, some different kinds of observations. So I've put it together, again, not an exhaustive table, of some of the types of observations that we're working with, and a couple notes in terms of challenges. There's a lot of observations of vegetation, but it's not always clear how independent they are or how to use them together. So for example, CF is providing a more direct measure of photosynthesis. It's also a noisier measurement. NDVI, or vegetation greenness, that's been around a lot longer. That's more the time integral of photosynthesis, but it's unclear, do we need to assimilate both? Which one is better? There's still a lot of debate within the community. And also there's a lot of challenge in using these old school kind of 2D methods that we've had for a long time with the newer biomass data sets we're getting from things like JEDI and ISAT2. So the bottom plot I'm showing is a nice highlight from our colleagues at JPL, their Carderon model, which is actually using a fairly simple modeling framework and trying to combine different data sets to estimate parameters and flux that aren't directly observable from satellites. So here we're looking at the carbon residence time as inferred from cardamom. So since I think we're short on time, I'm not going to say much about fire, but just to note that fire is a critical part of the carbon cycle. And right now, our fire models are largely separate from some of the DGVMs that we have implemented in catchment CN or other models. So bringing those data sets together, being able to couple more sophisticated fire models to the relatively crude ones we have in place in some of the big systems is quite important. And let's go to this one. This is, I think, important to go through, which is some of the terrestrial carbon challenges and opportunities. And this is really more challenges. I think land continues to be the tall pole, the really tricky part of carbon cycle reanalysis. We've made a lot of progress on the ocean. We've made a lot of progress on the atmosphere, and there's still quite a lot of work that needs to be done on vegetation. So I want to say first, vegetation models, even regardless of the level of coupling or data solution, can be incredibly sensitive to jumps in meteorological forcing. Rolf showed some of those examples of those jumps, and here's an example of that. It's running this through one of our in-house models, LPJ, and because of one of those jumps, just like killing off a lot of the vegetation in Africa, which is not great. So we have to be careful, even if we're not, coupling a vegetation model, we want to make sure that the meteorological information that we're providing in reanalysis supports this whole ecosystem of users and people who are running their own models. This is incredibly important. Other challenges in vegetation assimilation, there's a huge scale mismatch that makes it difficult to use observations directly, also makes it very difficult to validate the data sets that we do get from these models. The complexity of canopy rate of transfer means that DA is done with higher order derived products. That can lead to additional uncertainty. Highly simplified models may struggle to represent the reality of very complex systems. We have highly complex regional models, but finding the balance for this, and as in many other areas, remains very challenging. And the univariate approaches, we have a lot of examples where when we assimilate one thing, there's even some examples in the work Rolf showed, we assimilate one thing, we make something else worse. So really finding a way and a strategy to integrate many of the observations that we have in that table in the most sensible way? And how do we work together as a community? Because this is a huge challenge. So I'm going to end here. I'm out of time. But just to point out that, we're trying to go that I hope what we come away with is not necessarily it's going to take a long time, but what is the roadmap for getting from these disconnected cycles back to this complete picture? That's what we're missing right now. And I'll just leave this up here to note that I did kind of some of the same stock taking as Rolf, and I hope we'll get back to more of this in the discussions. Thank you.
Thank you. We'll just wait for if there's some questions, I guess. Yeah. Do you have any questions for Lesley? Yep.
There's a question online. Dan has his hand up.
Sorry, Ron, let's go to Ron in the, let's go to Ron in the room first, and then we'll go to Dan.
Maybe
Ron,
you just
can
get a bit
speak
closer to the.
Do it, just yell into it.
Okay, here
Fine.
we go. So the slide you had with the observing systems.
Yeah.
So it looked like, it was a bit hard to read, but it looked like there was going to be this golden period over the next few years. Yeah.
Fingers crossed.
24 through 27. Then are we sort of back to a very limited observing?
No, I
or
think,
is there stuff on the
no,
ground?
well, I don't think I think that it's just that those missions have not been put on the books yet. I don't think that there's any assumption that we're going to backslide because of the sociopolitical importance. And also the commercial investment is becoming huge in this sector. So that's, yeah.
The sense is that there is momentum to keep this.
Yes, I think the data-rich empire is going to be here to stay.
All right, let's go to Dan online.
Yeah, thanks a lot. That was a really interesting talk. I was wondering, you mentioned inverse methods. I was wondering if you could talk a little bit about complementarity or which of these problems might be better suited to one technique or the other. I guess I'm especially thinking about sparse observations.
Yeah, it's a really good question. There's been a ton of work, including from our colleagues at JPL, on inverse methods, particularly on the atmospheric side, trying to infer not just a change in concentration, but use the concentrations that we observe from satellites to infer a corrected surface flux. So there's a lot of opportunity there. Right now, again, those systems are kind of offline. Those aren't feeding back into an operational system. And they're also, again, like not feeding back to processes. The thing we would love is to eventually get to a point where we make a correction, and that helps us inform land and ocean models. So I'd say those are the big, that there's a lot of progress on sort of getting to net flux, but that attribution question is still very challenging. And also just pushing that into operations, there's a lot of logistical challenges and delays that we have to overcome.
Thank you very much. Thanks. So we'll move on to our next speakers. We have a double act now, Angela Benedetti and Antje Inness from ECMWF, and this will be a online talk.
Yes, thank you very much. I just share my screen and bring up the presentation. Right. So can you see it properly?
Yes.
Good, excellent. So yeah, hello everybody. I'm Antje Inness from ECMWF, and this is a shared presentation with Angela Benedetti, also from ECMWF. But to make it more simple, I will give the whole presentation and Angela will help with any questions you might have. So the talk will be about atmospheric composition reanalysis, and we are talking about this in the framework of the CUMS reanalysis. So to start off with, I just want to introduce or define what CUMS is for those of you who don't know it. CUMS stands for the Copernicus Atmosphere Monitoring Service, which is one of the European Copernicus services. It is implemented by ECMWF on behalf of the European Commission and provides a whole range of atmospheric composition or air quality information. We run a global model to produce global atmospheric composition forecasts, 5-day forecasts every day. We provide information about the ozone layer. We run an ensemble of regional air quality models in Europe to provide forecasts. We provide information about emissions and surface fluxes of pollutants and greenhouse gases. There's information about solar radiation, climate radiative forcing. And now, last but not least, we also produce the reanalysis of atmospheric composition. And all this is done by assimilating atmospheric composition data into ECMWF's integrated forecast system, obviously in addition to the meteorological observations. So CUMS has produced this reanalysis, which we call the CUMS reanalysis. And the period covered by our reanalysis starts in 2003. Currently, all the data up to June 2021 are publicly available, and we release data roughly every 6 months and are just about to release the rest of 2021. So our reanalysis contains aerosols, chemical pollutants, and also greenhouse gases. The horizontal resolution is 80 kilometers, and we have 60 model levels in the vertical from the surface to 0.1 hectopascal. Information about the reanalysis can be found in these two papers here. And there's also a whole range of validation reports on the website. And then all our data are freely available from the Copernicus Atmosphere Data Server. So you just need to go to this website, register, and then you can download the data for free. So we've produced this data set and assimilated a lot of air quality or atmospheric composition information. The data we assimilated were all retrievals. So for ozone, we have a whole range of instruments that we used. For CO, we used MOPIT, total column, the thermal infrared product. NO2, we used Skiamaki, OMI, and the various GOM2 sensors. Aerosol is largely based on MODIS, but we also used AATSR until 2012. And for the greenhouse gases, we used GOSAT and YASI. And then we also run our global fire assimilation system, the GFOS system, that gives us daily information about biomass burning and is based on MODIS. For the early part of the reanalysis, we used offline or reprocessed data. And then once we were running in near real time or close to near real time, we switched to near real time data. And that can have some impact on, unfortunately, on the quality of the reanalysis. So a data set like this, is as consistent as we hope we can make it, and can then be used to look at trend studies of, assess anomalies of various fields. And here we show one example of aerosol anomalies for 2021. And this is a contribution to the bump state of the climate 2021. That will come out at some point soon. On the left, you see the aerosol optical depth, the AOD anomaly for 2021 compared to the annual mean calculated over the years 2003 to 2020. And the features I want to pick out here are these red areas in the northern hemisphere. So we have positive AOD anomalies, and these are associated with the big wildfires that were burning in parts of Siberia and also in parts of North America last year in the summer. And this is really picked up by our AOD field. And if we look here at the number of days with extremely high AOD, which is defined as the above the 99.9 percentile of the climatology, you can see, that this really are the biomass burning areas in the Northern Hemisphere. We can also use our analysis to look at trends. This is another example of a contribution to the bump state of climate. This is a slightly earlier one, where we looked at CO. So here we calculate CO burdens from the reanalysis for the globe, and here for maritime Southeast Asia. And you can see changes with higher CO columns during the earlier years, and then lower values here. And you can see that 2015 really stands out with very high CO burdens due to a lot of fires over Indonesia. And we then also compare our data set with independent observations that were not used in the analysis. And here is an example of a time series comparing with TCON data at Park Falls. So the TCON data are the black dots, and our CUMS reanalysis XCO values are the blue lines. And you can see that the reanalysis captures the interannual variability and the seasonal cycle really well in comparison with the TCON data. And the last example I want to show is looking at the Antarctic ozone hole using our data set. And here we are particularly lucky because we also have the ERA 5 reanalysis in-house, which also includes ozone data. And the stratospheric chemistry scheme that is used in ERA 5 is the same as the one we use in the CUMS reanalysis. So if we just look at total column ozone, these two data sets compare really well. And we can use ERA 5 to extend our data set back in time to 1979. So we have a much longer time period we can look at. And we can then see how individual years, for example, compare to the overall picture. So we look here at the top left, we have the ozone hole area in the southern hemisphere. The range is shown in gray and the mean by the black curve. And you can see how the ozone hole usually develops during August and then reaches its maximum in October. And then the colors here show 2019 in light blue, which had a very small and short-lived ozone hole because of a very unusual stratospheric warming in the southern hemisphere. And then in red and blue, we have the two most recent years, which had very cold stratospheres, very stable polar vortex, and very large and long-lived ozone holes. When we look here at the ozone hole area, here is the ozone column minimum at the top right, and at the bottom left, we have temperatures that just confirm how cold the stratosphere was. So that's the data set we have, but we're now also thinking about producing a new reanalysis and hopefully a better one in the future. And the improvements that we could make in a future reanalysis are listed here, or at least some of them. So there can be advances in composition modeling. There can be advances in the data assimilation methodology. For example, we can improve the description of our background errors, or we are developing currently an emission inversion prototype at ECMWF. If that could be used, that would definitely improve the assimilation of short-lived species such as NO2. We can spend more attention on the data selection, quality control, and bias correction we apply. Any new reanalysis will use the latest version of our meteorological model, so it'll be improved there as well. We will use new compiled emission inventories, and then also take the latest reprocessed data sets. And then we will also explore the use of new observations, for example, LiDAR profiles or direct radiance assimilation. And I'll go through some of these examples now. This is an example that shows the impact of model improvements and also data improvements. Here we look at a time series, and we look at comparisons against AeroNet data. So it's a comparison for AOD. At the top, we have the bias, and at the bottom, we have correlation coefficient. And in red is the bias here from our CUMS reanalysis. And in blue is the bias that a control run, which was identical to the CUMS reanalysis without the data assimilation, gives us. And we can see, we have an improved fit to the data if we assimilate data. But the feature, or the curve I want to point out as well, is the green curve here, which is the bias from a previous reanalysis, the MUC reanalysis we produced. And you can see that the CUMS reanalysis has a smaller bias and also a higher correlation than the MUC reanalysis. And the MUC reanalysis has this increasing bias, which is not seen in our later product.
4 minutes.
Okay, another thing to consider is the impact that we get from changing observing systems. And here we look at ozone. On the left, the plots show you the various SBUV instruments that we used in the CUMS reanalysis. And the top always shows you the number of observations. So it basically shows where we have data from a particular sensor. And then we have the bias and the standard deviation of the bias. So you can see there's a lot of coming and going happening. Usually, or for most of the periods, the biases are very consistent, but then there, for example, are some changes here. And here at the bottom for NOAA 19 SBUV, you see that there's really problems towards the end when the orbit starts to drift. So we should have perhaps paid more attention and not used these data. We also used MIPAS and MLS. And especially for MIPAS at the beginning, we had to use some old near real-time data that we still had in the archive, because that was the only vertically resolved data set we had. But then if we look at comparison against ozone sondes, we see that we have much larger biases here during the earlier years. And we can also see that here in this time series where we just look at the bias between 25 and 15 hectopascals. So we really have problems here at the beginning. So it might have been better to actually keep some of the data for validation and only passive, and perhaps only use some SBUV data and MLS to produce a more consistent data set. Yeah, what we also explore is the use of new observations. For aerosols, we only assimilate AOD at the moment, so we don't have any information about the vertical distribution of the aerosols. But there's work ongoing testing the assimilation of LiDAR backscatter data. And this looks really promising. So here is the bias against Aeolus LiDAR data. And we can see here by the red curve is an experiment where LiDAR data are assimilated, and in black is one without. And we can see we really improve the fit to the data. So we hope that we can exploit this a lot more in the future. It still needs some work because there's a positive bias in the data globally, but the first results are very promising. And another point we hope to explore is the assimilation of radiances directly. Here, the assimilation of visible reflectances from MODIS is or was being tested. And we find that if these data are assimilated compared to a model without assimilation, we get a much better fit compared to MODIS AOD data. And it's very comparable to what we get when we assimilate the MODIS AOD data directly. The caveat here at the moment is that this works well over the oceans, but over the land it needs more work, because here the surface reflectance is very important and can lead to problems if this isn't treated properly. So, oops, that's one too many. To finish off, I just want to advertise the plans for our next reanalysis. So we hope to start a new one at the beginning of 2024. So the development work for this has already begun. And we will again go back to 2003, because this is really the period where a lot of the atmospheric composition data became available. We will use improved chemistry and also include a comprehensive stratospheric chemistry in this new reanalysis. With the latest IFS version, we will increase the resolution, use more new data sets, and also think about more carefully what we will do once we catch up with near real time. It might be better to stay a few weeks or months behind near real time and continue to use reprocessed observations. It does not look like our emission inversion prototype will be ready to be used in this yet. So I think this is just summarizing what I talked about. So I'll just leave this screen up and finish here. Thank you very much.
Thank you. So do we have any questions for Antje or Angela? Yep, do you want to come to the mic?
Hello, Antje. This is Kevin Bowman at the Jet Propulsion Laboratory.
Hello.
Thank you for the presentation. Obviously, one of the areas that of particular interest is air quality and tropospheric processes. Could you comment a little bit more about the current prospects and challenges for surface air quality, particularly like surface ozone, and the challenges or the observations you hope to be able to bring to bear to be able to improve our tropospheric understanding of ozone processes?
Yeah, tropospheric ozone is a tricky one, and we know we have biases. We have, I think, positive ozone biases in a lot of areas. The problem really is to get a handle on that part of the atmosphere. We hope that by assimilating total column observation in addition to stratospheric profiles, we can constrain this at least to some extent. But it is very difficult to get an impact near the surface. So we're trying to use some more data sets, but and also perhaps in the background error formulation, do some work there that improves it. But it is one of the big challenges at the moment for us.
Sergey?
Sergey Frolov. Thank you, Antje, for your great talk. Do you have any plans to combine production of Era 5-like reanalysis with composition reanalysis in the future?
There is some thought about this. I mean, this would be after the current phase of Copernicus, because there's no funding for that in the current phase. So it would be after 2027. I think one problem is that, well, first going back further in time than 2003 or so will be difficult for atmospheric composition, because there's some data for ozone and there's data for aerosols, but for the other species there really isn't that much out there. Also, if we include the chemistry, that comes as a cost. So if we ran a combined reanalysis, we might not be able to do the high resolution that they would want to use for the metrology, because it's just so much more expensive to include the full chemistry. So yeah, it's under consideration, but it definitely needs more thought and is some years away.
Can you comment on benefits that you might see from doing something like this?
Well, you would hope that including the chemistry will bring benefits to the metrology. I mean, we see that we have in our system interactive aerosols and interactive ozone. And definitely for some of the wildfires last year, the boreal fires, we saw that we had a better fit to SYNOP observations, 2-meter temperature observations in the run that did include the interactive aerosols. So yes, we hope there would be benefits.
I guess a quick follow-up question on the previous question. So for tropospheric ozone processes, do you think that going to a very high resolution, that's more like regional resolution, tens of kilometers, is that something that will help you to improve near surface processes, or it's just not the right solution?
It might help, but you have to be able to run the whole system and get a throughput. I mean, at the moment, we hope we can run 40 kilometers in the next reanalysis, and that will already be, I think, pushing the computing resources to get it through in the time frame that we want to get it through. So going to 10 kilometers, is a big step up again.
Okay, thank you.
Thanks. Just checking, we don't have any in the online?
Nope, we're good to go.
Okay, thanks. Okay, so we'll move to our last speaker of this session, who's Nguyen from University of Texas at Austin, talking about reanalysis with a focus on the high latitude.
Hi, everyone. Thank you very much for allowing me to give this presentation with the focus on the high latitudes. All right, thanks. And the focus here is primarily on the high latitude in the Northern Hemisphere. And my research focus primarily is in the ocean reanalysis. But I will try to give an overview for the ocean, sea ice, atmospheric, and related. I will have some comments related to some subsequent results relying on ocean reanalysis, for example, in the high latitudes. And sorry, is there a way to control this? Okay, so I was asked to give a PDF, and that's why I think this seems to be a problem. Okay. Okay, thank you. So first I put up here the one of the several goals of the workshop is to identify the scientific goals for the next generation of reanalysis from the various perspectives of atmospheric, oceanic, cryospheric views. And there are other things to focus on, but here I want to focus a little bit on the discussion of the scientific goals. So if you can go to the, can I try to see whether I can do it? Or yes. Yep. So on trying to identify the scientific goals and therefore what kind of reanalysis we want to do. So for example, whether our goals are on forecasting, prediction, projection, or for climate research. And then depending on that, obviously, do we want to maintain as the workshop goals mention what kind of consistency we want? Do we want to use the products for budget closures, or do we want to use it to estimate the uncertainties in both the outputs and the inputs of the reanalysis? And then depending on that, whether what kind of techniques we will be using. So for example, whether we use 3D, 4D VAR in the filter approach or the smoother approach, and depending on that, what kind of applications that can come with it. So I give an example here of the various ocean and sea ice reanalysis currently. This is not an exhaustive list at all, but it gives you sort of an impression of what products are out there at the moment. So for the regionals, highlight in blue, there's the Arctic Subpolar State Estimate Release 1 at UT Austin, which is based on the ECHO Adroit framework. There's Topaz 4 from the Nansen Center, the POMAS, which is the sea ice reanalysis based at University of Washington. And then for the other more, for example, global reanalysis of oceans that include also the high Arctic. And then you can see the list here. I don't need to highlight all of them, but some of these are fully coupled, and others, they also rely on other reanalysis products as their input. So for example, on the right here, I show, then we rely on ERA Interim, ERA 5, MERA 2, ERA 55, and SAP Core 2, etc., the various other reanalysis. And so it depends then on what kind of things you want to achieve, what kind of inputs you need. And so I developed that a little more in detail. And here I only give as an example of one of those reanalysis. This is the one we produced last year, the release one. And it's the first of its kind for the Arctic, Subpolar, North Atlantic Ocean sea ice reanalysis. It's multi-decadal, but starting in 2002. And the reason I think was related to, I think, the previous speakers as well. Sometimes it really depends on when the data is available. And the goal for this reanalysis was for climate studies, and it was done by fitting to a very diverse stream of data sets of 10 to the 9 satellite and high latitude in situ observations. And the model dynamics in this case was used as the interpolator where there's no data. So the technique used here was the adjoint-based non-sequential approach. And therefore it maintained the dynamical consistency and enable budget closures. And it was achieved by accounting for uncertainty in input parameters such as the surface forcing, internal mixing, initial conditions, etc. But I use this only as an example for the kind of bias you still see regardless of what you try to do for the high latitude in the oceans. And that's shown here. Hopefully. Thanks. This is shown here as some of the still outstanding biases that we still have in our reanalysis. So on the right, the figure shows sort of the map view of the Arctic Ocean, where the gold wiggle lines are the available subsurface in situ observations that we have to try to constrain the hydrography in the ocean, in the reanalysis. And one of the key issues we tend to have is that we have the observations where we don't quite have, in order to constrain some of the very important parameters or dynamics. So in this case, what's shown in the blue arrows, for example, is what thought to be the circulation of the Arctic. And so you can see actually the observations are elsewhere on the interior, which is much further downstream than where you need in order to constrain the dynamics. And for that, and among other reasons, so then regardless of the technique you use in the high latitude to try to do reanalysis for the ocean, you still end up with a bias in, as highlight here, for example, in the lower left figure of the mean normalized misfit in salinity for the Eastern Arctic, where you can see there's very little data, that the misfit, normally you try to obtain within ±1 uncertainty, and that's sort of considered convergence. And here the persistent bias are in the order of 10 to 20 still. And I want to develop this sort of persistent error bias a little further by then connecting it to, next please, to the input parameters that we have, for example, for some of the uncoupled ocean reanalysis. So for example, this is some recent literature reviewing various atmospheric reanalysis in the high latitude in the Arctic Ocean from a couple of papers here. And I give only as an example here for the surface 2 meter, the 2 meter air temperature as a spread between the various products for atmospheric. So it spans from NCEP and CAR, ERA, GRA, and then the MERA2, for example. And one of the key things you see here is that in the high latitude in particular, we really have a problem that some of the largest errors in any kind of reanalysis, in this case atmospheric I show here, is there in the Arctic. And what is shown here, for example, is a spread of up to 6 degrees Celsius in a mean 2 meter air temperature over the winter season. And you can kind of imagine, if you have this kind of input into your models, then just from that spread alone, you can imagine the widespread of the reanalysis result that you get. And next, please. And so one of the key things I want to then try to push here is, again, to try to understand what we want to develop next for the high latitude in terms of improvement. And there's a recent paper in 2016 by Goddard on trying to understand systematic error and improvement for reanalysis in the Arctic from an iArctic project. And one of the key things they find out, which probably is not a surprise to the people in the room, is that compared to the mid-latitudes, the high latitudes, the Arctic has a paucity in situ observations. And in addition, both the infrared and microwave satellite sensors have difficulty in profiling the low atmosphere due to the presence of snow and ice in the high latitude, and that there's not enough satellite observations up in the high latitudes. So the key to understand this is then, I think someone also, I think it was Rolf in the first talk, who mentioned that when you don't have observations, then a lot of what is considered reanalysis is actually just a forward unconstrained run. And you remember from the MERA plot that Rolf showed that can have really high bias, for example, in precipitation. It's not surprising that I show in the previous slide of the errors or the bias that you see in the reanalysis. And then we have to worry a little bit now about trying to use these analyses to study trends, for example, because I think several speakers also mentioned the effect of having observations or no observations and what that can do to the analysis. So in the Arctic in particular, then you end up with introducing actually artificial trends, which is, for example, outlined in one of the paper by La Liberté and Kushner, where you see trends due to just the analysis increments alone that you establish that kind of trends in there. Next, please.
5 minutes.
Yep. So some of the consequences of the reanalysis increment here, I try to give just a very, I'm sorry, this is a very elementary figure, but I really want to highlight the details that somehow I think is still not, that's still quite being overlooked in the community while trying to use analysis to do budgets and studies of changes. So in the upper right, I show now again, for example, imagine we take in the bias from the atmosphere as our forcing for a sea ice. So the block in gray at time 0 is meant, for example, the analysis step for a prediction of the sea ice, but now you have the air temperature coming in, so you melt it. So the next HP for prediction is that you have thinner sea ice. And then imagine at that time you have an observation only where the yellow block is and not elsewhere. So depending on your approach, for example, on the lower left block, if we were to do sequential 3D 4D VAR, this is very basic, sort of crude example, but you can see because where you have the data, so therefore you can have an increment, analysis increment there, and therefore you can introduce the correction there, but you don't necessarily take into account other locations. And on the bottom right, the other approach, for example, that one can try to think, that's what we also try to do, is understanding that there's errors in the inputs, and therefore we can make the adjustment on the input themselves, which has a larger scale, for example. And therefore, in your next iteration, essentially, you would have a prediction, you would have a next improvement of the sea ice. And it's not a direct improvement, obviously, where the locations are due to the model non-linearity, among other things. But at least on the bottom right, you try to maintain the dynamic consistency within the equations of the models. Whereas on the bottom left, you can see that here we introduce, so not only that we know ahead of time that we have errors in the input, but now we also introduce extra heat sink, and therefore just from the figure alone, you can see we introduce artificial source and sinks and trends, etc. And even though I highlight here, but it's actually seen in published results as well. So show on the right, for example, is a figure for Topaz 4, the product as the presence of data. So this is for SST, sea-surface SST, where when there's no data, there's obviously bias in the solution, and then in the reanalysis, and then when there's data, the bias is gone or significantly reduced. But then the problem one can potentially see here is actually that you have a trend that you're introducing in. And this can become critical when one then try to use these kind of reanalysis to study changes, for example. So this is in the literature that recently, or not recently, but historically, ocean reanalysis in the high latitudes are known to have biases, and therefore, in general, they are not as useful for contribution to the IPCC. But then one of the approaches for trying to see whether we have improvement in the ocean reanalysis is by evaluating these products only where there's observations. And already I highlight the problem that if you only do that, then you will get a good fit where there's observations, but then you might introduce trends and biases elsewhere. But there had been studies that then once they have shown that they can improve the reduction of the biases, that now it can be used to explore interannual decadal variability of global and regional ocean heat content changes, for example. So for me, I think these are the things we need to maybe bring to attention, that it depends on what we want to do for the scientific content or how to use the products, whether what kind of improvement we think we should need. And I think that's actually my second to last. So just this one, I highlight some of the questions that were, that were asked of us to answer. For example, what are the significant barriers? And I would say for the high latitudes, some of the key barriers is that the analysis increments can be quite large in space and time. And it's quite unclear what kind of changes we see in the product. How do we interpret them? And it's quite clear already that there's significant lack of observations in general in the high latitudes, and therefore they become large errors in our input system, depending on whether you have a fully coupled or whether you depending on one to improve the other. And all of that had large consequence for trying to estimate the biogeochemistry and ecosystem reanalysis, because all of that depending on the ocean states or the atmospheric states, etc., as the physical process for driving. And some of the suggestive thing I try to put down, for example, that some of the things we can try to improve is the parameters estimation or the model physics. For example, I think Rolf mentioned that some of the parameters were from lookup tables. So I think some of the things we could try to focus is also to use the system to improve some of that input parameters to see whether it can improve the physics rather than trying to only adjust the state variables themselves. And just to outline that a lot of the high latitudes in particular, there are just so many parameters into the model themselves that are uncertain, and yet they have so large sensitivity to the trajectory of the model that hopefully that can be the focus of some of the development going forward. That's it. Thank you.
Thank you. Do we have any questions? I guess I had you focused a lot on the observational issues, and then at the end you mentioned the underlying model issues. I guess I'm wondering, do you see reanalysis kind of feeding back into model development with, you know, understanding where the models are going wrong with the analysis increments that you see and things?
I think I was trying to think more in the sense of whether to try to understand the underlying physics, so that, but I understand that it depends on the priority, obviously. For example, for forecasting or projection, sometimes the improvement of the model physics alone doesn't allow you for the time, because it's more of a research question. But I think to try to understand the underlying physics so that we can then have a better understanding of how to make the next predictions, that I think is it can be of an improvement compared to trying to just look at adjust the to achieve the analysis increments themselves, because essentially you adjust the state variables without really adjusting or improving the underlying model physics. So once you don't have data, then you don't have that increment anymore. So then the model will just proceed based on the imperfect physics that you have in the background. So I think it was more that I was trying to.
Do we have any questions online? I guess if there are no more questions in the room, we could just move to the general discussion, which we can have, I think, for about 10 minutes. I know we missed out on some questions for the first talk, so I don't know if you want to, did you have a question? Would you like to ask it now?
There is also a question online, so we'll take Arun and then we'll go online.
Oh, okay.
Thanks, Ayla. Rolf, you were mentioning CPC a couple of times in the gauge analysis. So I'm from CPC, and there's Lesley Suzaki. There's question I had was, I mean, I can't recall anyone retiring and that impacting the. So that is, it's true? Okay, so you're right.
Can you talk in the microphone?
Yeah,
You have to
can
talk
we
on
use the
microphone.
mics for the people online?
Yeah, you can, maybe, Lesley, you know better than I do.
Sid Katz did retire during the COVID, but I don't think things have taken over, but I don't think he knows that things have changed.
I guess you did point try to contact somebody in CPC and try to figure it out. And I wonder if you got the right answers or what the issue was, and we try to resolve that. And I mean, that's the part of the collaboration, the third objective of this meeting.
Yes, we did try to get in touch with someone, but because of the pandemic, that was complicated, I guess, because everyone was just kind of lost. I didn't mean to pick on CPC.
No,
to some extent, it is
good.
just a general problem.
That's the part of the
You
collaboration.
cannot have these things on, you cannot have these things on autopilot.
Correct.
Someone needs to look at it, and that's not different for what we're doing. I mean, we're putting out narrative, we're looking at it, but every once in a while we mess up.
Of course. I mean,
So it's just the gauge record is complicated because it's not complete. And the satellite record does seem to help. So the move to iMerge, which relies on the same gauges, it's a newer product. The CPC product that we are using is great because it's the only product that comes with the required latency and includes gauges.
Correct.
And that's unique.
Right.
I mean,
So Dan asked about the different kinds of methods that we use for carbon cycle assimilation versus that might be appropriate. And this is valid for both carbon cycle as well as for composition assimilation, such as used in air quality. One of the first things to consider is that the boundary value problem is a first order problem in carbon cycle science. So you have to get the fluxes into the atmosphere correct. That drives us towards inverse modeling techniques, which can use either 4D variational simulation techniques. This is popular, has been used at NASA as well as many other areas. Of course, it requires an adjoint. They're also used 4D ensemble common filtering techniques, which have also become quite popular. And then as well as what is called analytic Bayesian techniques. These are simply direct calculations of the optimal estimate. So it's explicitly calculating the sensitivities of observations to fluxes and then explicitly formulating the matrices for those. Each one of those techniques has their strengths and weaknesses, but I think some important considerations is that the window, whereas for a lot of Earth system applications, particularly weather, the shorter the time window, the better, because you're trying to capture fast processes. For the carbon cycle, many of these processes run at much longer timescales, and conservation properties, such as the amount of carbon that's in the atmosphere, is extremely important. So if your simulation window is short, then you run into discontinuities between those windows, which can lead to losses of carbon. And since you're counting carbon molecules is extremely important for understanding climate forcing as well as attribution, these become more paramount considerations relative to just being able to get an estimate. Concentrations are also important, and Lesley's work of Brad Weir's been doing for 3D VAR uses those techniques, but this creates a divergence in some of the techniques than what you might see in some other areas. Thank you.
Thanks. Do any of the speakers have anything to comment on that? Okay, do you have a question?
Kathy Smith from NOAA PSL. This question was sort of inspired by the high latitude talk on observations. It seems like the observations often aren't in the right place for long enough. And it was a little more obvious for the Arctic, but it's true probably for the other sorts of observations where you have to really change them or analyze them to make them match or work in these reanalysis. So is there, probably very naive, but is there any way that the people doing the reanalysis can influence the people taking the observations? I mean, I could see it happening in the Arctic. I'm not sure about anywhere else, but it seems like it would be helpful rather than, you know, focusing on, say, short-term observational experiments like Mosaic or something like that.
Yeah, thanks. Seems a good point. I don't know if Anne, do you want to comment on that for the Arctic case or?
I think that's always been a push for our case, but I think it's more a technological challenge. So the environment is very harsh. And I think often we find out that there are certain things that are easier to observe than others. So for example, I give an example of ocean. In the ocean, I think we have instruments to measure TS, for example, but the ocean currents throughout the ocean, that's actually not something very well observed, even though that actually would really help to constrain the circulation. So ocean mixing, that's something that everybody knows that you have a parameter in the model, for example, to that drives the mix, the internal mixing. But then how to make that kind of observation, they're excessively expensive. And I think, so I think it would require campaigns that are of different scales or a strategy for doing that, because what the current observation, normally you would have an excess, I would say, for example, of certain type of parameter of observations that are not necessarily going to directly influence the. And I think for the atmosphere, again, the satellite requirement, whether it can be of high latitude orbits, because then you don't have as much crossovers at, in the low latitudes, etc. I think these are the requirements that probably needs to be. Let's say if you want to put.
Okay, seems like if no one has any more questions, it's about time to move on. So I think we're having. Oh,
we have one more comment from Kevin in the chat. Kevin, do you want to ask it?
I think I can read it out loud real quick. Yeah, just a general question. How do we account for uncertainty both within Earth system components and between those components? So perhaps this is something that we can save for the breakout group discussion. I know that we're heading into break, and I do want to give some instructions on that.
Okay, good afternoon. My name is Patrick Heimbach from the University of Texas at Austin, and I'm pleased to open the second round of presentations. We'll have 3 presentations. Each will be 20 minutes, well, 15-minute presentation plus 5-minute Q&A, and then we'll have another 20 minutes afterward for discussion. So with that, I'm very pleased to introduce our first speaker, David Richardson from ECMWF, who will present about probabilistic products for numerical weather prediction. Thank you, David. And you will get a 5-minute warning from Jenny, and then after 15 minutes, we'll do a Q&A. Thanks.
Thanks very much. So I hope you can see the right screen. And I've gone already one slide too far.
Yes,
okay.
We see that. There you go. Perfect.
Thank you very much. So yes, probabilistic products for NWP, and I guess implicit in the title is how we use reforecasts and reanalyses and reforecasts in our operational everyday products. And because I'm from ECMWF, the examples here will be from ECMWF's forecast. First of all, a big thanks to my colleagues at ECMWF, Tim Hewson, Frederick Wittard, Ivan Sonevsky, and Erwin Jota, who helped me at very short notice to put this presentation together. So just to mention our forecasting system, as I said, the examples come from our ECMWF operational forecasts. So we run our high resolution forecast twice a day, but the main examples I'll be showing come from our ensemble forecast system. It's a 50-member ensemble that we run twice a day, every day, out to 15 days ahead. And then twice a week, we carry on running it out to a month ahead, or even a month and a half ahead nowadays. I just note that the atmosphere is, in all forecasts, it's coupled to a 3D ocean model, and it's also coupled to an ocean wave model. So although my examples are all from the atmosphere, they apply equally to the ocean waves. And it's important that we have reanalyses for all components of our forecasting system, in case I forget to mention that later. And then we also run seasonal forecasts everything I say applies equally to the seasonal forecast, but my examples are just from the medium and extended range. And mostly I'm focusing on some of the products from our ensemble forecasting system. So we have a whole range of products that we generate every day for our users, which are mainly our weather forecasters in our member states. And these present different aspects of the information in our high resolution and ensemble forecast. It's important, essential, of course, to represent the uncertainty in the forecasts. That's why we have the ensemble in the first place. And we look at all aspects from the broad evolution out to 2 weeks ahead. That's our main focus at ECMWF is forecasts out the 1-2 weeks ahead. So we're looking at changes in the large scale flow, changes in weather regimes, but then also in the earlier part of the forecast, highlighting potential for severe weather events wherever they occur around the world in the next few days. And then on the monthly and longer time scales, we're again looking for how the weeks ahead are going to evolve in the broad scale. We have a whole range of forecast products, and in the medium range, so for the first week or two, a lot of them really are the direct model outputs. So the standard 500 hectopascal height, sea level pressure, precipitation, temperature, etc. But even then, it helps to put things in the context of some sort of climatology. And so the example on the screen here is just a point forecast for Reading in the UK, where I'm based. This was made from last week, and it just shows you the evolution, summarizes the evolution at Reading of the maximum temperature forecasts on the bottom for 2 weeks from a week ago, and the evolution of the near surface wind speed. And you see that it was a bit of a windier week last week, a little bit cooler, but it's been getting warmer this week, and the temperatures will get to a peak on tomorrow and then drop off slightly during the rest of the week. But even here, it's very helpful to be able to put the current forecast into a climatological context, especially if you're not so aware of the climatology of where you are. And the right-hand figure just puts it's the same, the scale's a little bit different, but the shading underneath shows the climatology for Reading for May for May time, and it helps immediately to put the temperatures and the winds in context of how climatologically unusual the weather is. That's maybe a very nice thing to have just for the general weather forecast, but especially when you move on towards extreme weather, it really becomes essential to be able to put today's forecast in some sort of climatological context. And this is just one example from an extreme rainfall case in Europe last July, especially in parts of Germany and Belgium, and there's more about it in one of our recent ECMWF newsletters. But there's a very extreme rainfall over 2 or 3 days, and that caused some massive, serious flooding as a consequence. The map at the top right shows the observations, and the little black box shows the most extreme rainfall area. And the examples here just show a couple of ways of using the reforecasts, the reanalyses, and then the reforecast. So this picture at the bottom is just a zoom in and is actually showing our ERA 5 reforecast reanalysis 48-hour precipitation for the time of maximum rainfall. And just to show how extreme that is in the context of a climatology, the histogram plot on the right-hand side here is showing the distribution of 48-hour total precipitation over this area indicated in the little yellow outline box here, over all cases we have from our ERA 5 reanalysis from 1950 to last year. So you see the distribution with relatively very few cases of more than 40, 50 millimeters averaged over the area in a 48-hour period. And that puts the observation from this 2-day spell last summer into context, because the observed rainfall, or not even the observed rainfall, but the ERA 5 analysed rainfall for that 48-hour period was over 100 millimeters. So it's far, far outside the extreme that ERA 5 has measured over the last 50 years. So that puts the event into context. And then to put the forecast into some sort of context, we have on the left-hand side, forecasts for the same box of the rainfall. The box and whiskers show the ensemble forecasts made twice a day, every day from the 2nd of July until just before the event, which is on the 13th, 14th, 15th, 16th of July. So each box plot shows one ensemble forecast, and you see as you get closer to the event, the indication for it being more and more extreme, and the little red climatology box here is in a sense a summary of this plot on the far right hand side. It shows the climatology, and although we maybe didn't get the observed total rainfall as observed, right, you see a very strong signal from a few days before that this is going to be a really extreme event in the context of climatology, whether it's observed or model climate. And the picture we have in the middle is one of our very popular forecast products, which is known as the Extreme Forecast Index, which is actually a summary measure of the difference between the ensemble forecast of the day and the climatology, the model climatology, which we get from the reanalyses and then running reforecasts from those reanalyses. And this is just another example of this Extreme Forecast Index. It's a great way of summarizing the potential of extreme weather because we can plot global maps of it. It's a number that ranges just between 0 and 1. When it's 1, every single ensemble member of today's forecast is beyond the climate distribution. When it's 0, your ensemble distribution of the day is basically representing the standard, the climate distribution. So it gives you a very easy heads up, and then you can delve into more details of where there's potential for extreme weather. And this is one of our most popular products with our forecasters, just to give a heads up a few days in advance. Another thing I want to mention is the importance of running not just reanalyses, but reforecasts, especially when you get into the extended range. And this is an example of the model, forecast model bias. So this is looking at a weekly mean for the forecast for 3 days ahead. And this is showing the model bias, so difference between a 3 week ahead forecast and the analysis for 2 meter temperature averaged over 25 years of ensemble extended range forecasts. And of course, for those 25 years, we need to start all our forecasts from an analysis. So we need the reanalyses just even to be able to understand the model bias. But the point here is that the signal that we're looking for is often of a similar magnitude to the bias that we have in our model, the model drift that you get 2-3 weeks ahead. So it's important to get the signal that we calibrate the model, and we can only do that by having the model climatology based on forecasts and reforecasts. So in fact, what we do operationally every week is that we don't just today run the ensemble of the day, but we rerun our forecast model starting from a reanalyses back over the last 20 years so that we can generate a model climate appropriate for the forecast range that we have, and then we can put all our forecasts in the context of the model climate and account for model drift and systematic errors. And that allows us to present all our extended range products in terms of anomalies, having taken account of systematic errors, model biases, and the model climate. And there's a couple of examples here, just on the left-hand side of a weekly mean temperature anomaly, and on the right-hand side of the probability of being in the upper third of the model climate distribution. Or we can look at quintiles and deciles of the climate distribution to give a bit more indication of extremes. And again, in the extended range, we can also, since we've got the full model climatology, we can look at the extremes. We can look at how far today's ensemble is in different ways towards the extreme of the model climate. I just want to show a couple of other examples. First, again, to make the point that we have an Earth system model, and it's not just the atmosphere that we're forecasting and needing reforecasts for. But at ECMWF, we also run a global flood forecasting system on behalf of Copernicus. And so for that, we need to forecast stream flow or river discharge on large river basins around the world. And again, looking for potential for flooding, the forecasts are often presented in terms of likelihood of return periods. And of course, for the return period, we need to have the climatology again. Observations, especially for hydrology, are very limited, and so we also rely very much on a reanalysis, a hydrological reanalysis, to be able to put our forecasts into context. And again, this is just one more example of a validation and verification study that shows how important it is not just to have the reanalysis, but to take account of model drift, and so to run a whole set of ensemble reforecasts for our stream flows so that we can take out the rather significant model forecast drift. And the last example of an application is looking at the broad scale regime transitions. So in our case for Europe, we're looking at the NAO blocking regimes and the potential for moving in the next days, weeks, even months ahead from one regime type to another regime type, which gives us bounds on the general type of weather and potential extreme weather that we might get. And this is just looking at the blocking and NAO pattern for up to 10 days ahead. But the important thing, thinking of the reanalysis and reforecast for this, is that we need to have our reanalyses to be able to understand the forecast regimes, to define the regimes in the first place, and then to be able to project our current forecasts onto these regimes to see how the systems evolve. So again, we couldn't have a product like this if we didn't have the reanalyses and then the reforecasts from which to generate the patterns. And I will stop in just a minute. So this is my last slide. So this is a very quick run through of some of the forecast products that we have and how important, even in the operational forecast, it is to have reanalyses and reforecasts. So at ECMWF, and especially for our users, they really appreciate the products we have, which use in the operational forecasts information from reanalyses and reforecasts. The examples I showed from the medium range put today's forecasts in the context of climatology of a model climate. And that's especially important for when you're trying to forecast extreme events, and especially around the world where you maybe don't have a precise idea of just what are extremes in different places. But having the climatology and things like our extreme forecast index really help in that. And then in the extended range especially, it's really essential to be able to account for your model bias, which you therefore need to be able to understand, to calculate, and then to take account of in your forecast products. I didn't talk very much about the other aspects, the verification, case studies, model understanding and diagnostics, but we use reanalyses and the reforecasts in all of these, and all the information we get from that is also important on the practical side to pass on to our users so they understand the capabilities of the forecasting system. And just a few final points why I mentioned reanalyses, reforecasts, why those are so important. I mean, to some extent, you can calibrate your system against observations, but of course, globally, they don't have the full coverage. We can generate our extreme forecast index for all sorts of model parameters. The example in this picture is for water vapor flux, or we could do the same for CAPE or other convective indices, for which we don't obviously have observations. And of course, the model climate is different from the observed climate. And if you're trying to pick out what the model's trying to tell you about an extreme, you really want to look at that in the model world, so you can see how extreme your current forecast is in the context of everything which your model is able to do. And at the shorter range, this takes account of important things like representativeness. At the longer range, you're accounting for systematic errors, model drifts. And so we need reanalyses, and based on those reanalyses, reforecasts, and that really gives us a huge range of extra forecast products that we can generate and are very much appreciated by our users. And I will stop there. Thank you very much.
Thank you very much, David. We have time for 1 or 2 quick questions in the audience. So, yep, please, Sergey.
Thank you, David, for your great talk, and especially in such a short notice. Can you comment on the length of reanalysis that you need to support this kind of products? And maybe follow up on it. You know, there's definitely like the main reanalysis 79 onwards for ERA, and then there was an extension. And can you actually detect the quality of their reanalysis in the type of products you use from the first versus the second period?
So for the operational forecasts, we base it mainly on a 20-year reanalysis or reforecast from the latest 20 years. And that's partly because it reduces the trends that we have. So it's the most homogeneous sample we have if we take the last 20 years. There's also a cost involved. So we can't afford to run our reforecasts back over the full 50 years of the reanalysis. So we focus on the most recent years, which are the closest to the operational configuration. So we're not too much affected by trends that we know within the reanalysis, within the data assimilation system. To balance against that, of course, the further back you can go, the bigger sample you can get, and that has potential benefits as well for looking at extremes. So it's a balance, but at the moment, we use the most recent 20 years as our best compromise for the forecast products.
Do you see examples where the 20 years is not enough samples and you need to go furthermore, or?
Yes, we get around that to some extent, especially for the longer range, by running our reforecasts as ensembles. So by the time you're looking at day 15 of the forecast, we run a 10-member ensemble for each reanalysis start date. And so we start to generate a bit of extra sampling by doing that. So we have our forecasts are spread out over 2 weeks, and that gives us somewhat improved sampling of the extremes.
Okay, thank you.
Yeah, thank you very much. I think we need to move on, but David, I hope you'll be able to stay on for a bit. We'll have at the hour, we have another 20 minutes for a general discussion. So thank you very much.
Yep.
And our next speaker is Chiara Cagnazzo from, again, ECMWF and also Copernicus. And she will be talking about climate services providers.
Yes, good afternoon, good evening. Sorry, I'm trying to share my screen. I'm quite slow.
Yep.
Can you see my screen in full?
Yes,
okay,
we
I will
can.
try to put you down here. Okay. Okay. So good afternoon, everybody. And I'm Chiara Cagnazzo, and I work in the last 2 years in close contact with many users of the Copernicus Climate Change Service. And in practice, the users need to develop climate-related applications that are based on different typology of data. And the reanalysis are one of the most used products. I'm also sharing this presentation with my 2 co-authors, Hans Hersbach, who is here. He's the lead of the reanalysis group at ECMWF, and also Francesca Di Giuseppe, who is expert on the fire products. So, of course, I would like to thank all the C3S colleagues. So, first of all, I would like to start this presentation by mentioning those 2 key messages that we would like to bring to the discussion. The first one is that from a climate application perspective, the significant advances and the recent evolution of reanalysis have contributed to make it one of the key data sets in several climate applications. And I will bring you examples coming from the climate energy community. And the second message is that we would like to mention the experience at C3S about how important is including the user requirements in the design of the evolution of products such as reanalysis. But you will have more information about that from the presentation of Annabelle on Wednesday, but also I'm not going to present anything about the key elements of C3S and the Copernicus program, because you will hear about it also from Carlo Bontempo on Wednesday morning. So in this presentation, we are going to show you on the one side a few climate-related applications that are based on the ERA5 reanalysis. This is one key product, of course, of C3S. But we will use also those examples to have a kind of a reflection on which is the added value, the gaps, the limitations in the use of the reanalysis coming from this different community of users, but also how in the new reanalysis systems, ERA6, we will try to address some of them. So a very quick overview about ERA5 products, because all applications that I'm going to show are based on ERA5. ERA5 is in production at ECMWF for C3S. It has replaced ERA interim, and the main characteristics is that it is available at about 30 kilometer resolution in space. It has hourly outputs and an uncertainty estimate at the larger scale is available through 10 members ensemble data assimilation. It is available close to real time, let's say with 5 days latency to the public users, and it is available, the data are available back in time to 1950. Of course, highest quality over data rich area. Now, this is the first example that I would like to show you, and this is based on one example of let's say, typical applications that make an extensive use of reanalysis products, and those are the climate monitoring applications. And the example here focuses on one variable, that's the wind over Europe, and it makes use of ERA5 data, and it comes from the last European State of the Climate report. So what you see on the left-hand side of this slide is this annual average anomalies of the 100-meter height wind speed in 2021 relative to this 1991-2020 reference period. So this year, 2021, the annual mean wind for this year has been quite below average in the north and the central Europe, in this band covering UK, Ireland, but also to Germany and Czechia. And in contrast, the southern Europe saw kind of stronger than average prevailing winds. And this is, of course, is an annual average, and the magnitude and the spatial pattern of the wind anomalies change throughout the years. But in order to put the year 2021 in context, I show here now the ranking of the year 2021 relative to the other years that are available in the ERA5 dataset, so from 1979 onward for this specific metric. So the dark blue areas show that the regions like, for example, Ireland, UK, Denmark, are experiencing the lowest or the second lowest average annual wind speed in this 43-year data record. So, but why this information is important and is relevant? Well, of course, these anomalies have had an impact on the wind power generation in Europe for this year, because of course, wind power generation is highly sensitive to variations in the wind speed. So this figure now comes from the same report and shows the potential impact of these 2021 wind speeds on the national wind energy production in Europe. And this is a metric that is assessed based on model estimates of what we call the capacity factor that is run on the ERA5 reanalysis available in near real time. The capacity factor is this ratio between the average power delivered by the wind turbines and their theoretical maximum power. So this result shows in practice that these annual onshore and offshore capacity factors for different countries have seen quite important and the largest negative anomalies. And somehow, let's say, this is really consistent also with what the wind energy sector reported on the actual production. And here we can notice that the most affected countries are also the countries that are the largest wind energy producers. But monitoring is also an example of where, for example, the wind speed is a crucial element. But this because, of course, the wind power generation is reaching a very high growth rates at the global scale. But the wind speed from the reanalysis is also used for planning, for example, planning sites that are the best suited for investment in new power plants. And this is an example that comes from the International Renewable Energy Agency. The time series that you see in this figure show the power generation capacity in several countries in Africa. And this is expressed in gigawatt from different sources. I'm not going into the details, but the time series is an estimation of this existing and committed capacity based, of course, on what exists, on what was committed in 2015, the lifetime of a plant and the time required for building plants. And the red line now is instead the estimation of the projected peak demand. And you may see, I'm not sure if you can see the numbers on these slides, but you can see that there is somehow at the end of this time period, that is 2040, a kind of a mismatch or a deficit between the projected peak demand and the existing and committed capacity in 2040. And in practice, this implies that there is a need for a capacity expansion. And this means that there is a need for new technologies to close the gap. And of course, solar and wind are included technologies that need to be represented in details. And so there is a need from this community to generate an open source model that, and of course, databases that are model ready for solar and wind. Now, this is an example of this database that I was referring to, and this is again based on ERA5 reanalysis. This is now a map of the locations of sites that are estimated to be the best candidates or the most attractive for investment in new solar and wind power plants. So that's a very interesting study that takes into consideration not only the average wind and solar data, but also their daily to seasonal variability and the distance, for example, from existing grid and road infrastructure. So to summarize, the locations where we have the strongest resources may not necessarily be the best candidates for investment in new power plants, because, for example, the distance from existing grid and road infrastructure or the temporal variability of the power generation are also very important elements. This is, of course, an open source data set built on the ERA5 reanalysis, but not only. The ERA5 solar irradiance and wind speed are bias corrected and spatially downscaled with respect to other data sets. In this case, we are referring to what is called the Global Wind and the Global Solar Atlas. Those are 1 kilometer data set. And other data are also used in these computations, like population density, elevation of the sites, slopes, land use, protected areas, distance from roads and grids. So the hourly information is then used to estimate this kind of diurnal variability of the power generation through these estimated capacity factors, and the seasonal variability is also added on top. And of course, in this case, the hourly resolution of the reanalysis is one key aspect, but also the fact that in terms of diurnal variation, ERA5 outperforms with respect to other reanalysis data. So we have asked our users from their perspective some of the key questions that were relevant for the discussion. And let's say one of the first requests from those users is, of course, going for a high resolution at the global scale. And for some of those applications, as you have seen, this is now downstream of the reanalysis through statistical or dynamical downscaling. And addressing this issue is one of the aspects of going toward more realism in the next generation reanalysis. So this typology of users are users that are interested in having a full, good and complete picture, accurate representation of a specific component. Also, reducing the bias is another key aspect, and especially the bias in the wind is very important. But also bias in solar radiation, precipitation, and the snow cover. And of course, this is especially important in complex orography areas. And this means that we need to handle systematic errors. And you will have a presentation on this tomorrow by Patrick. Our users, for example, told us that when the 100-meter vertical levels in the wind was distributed as a product, this was really a big change for them, like a big leap forward. And of course, it is possible to do the interpolation from the 10-meter winds through the power law, but this was generating important errors, up to 50% in certain areas and different heights. So having more model levels available and tools to interpolate is also an important requirement for the users. And in some cases, but this is less relevant in this context, a longer time series has been requested. However, because of the data poor area may have, of course, an important impact on the quality of those products, this still has to be evaluated. We asked also about which observational data sets are required. I have no time to go through that. I would like just to mention the barriers for quantifying uncertainty in their specific field. And in practice, of course, one of the things they need to do is that they have to have information on the subgrid scales. And so users need a way to associate kind of an uncertainty in their derived products. And of course, the information that comes from ERA5 is not enough for their applications, but also suggested to add statistics like root mean square biases with respect to reference data sets. Of course, this is possible to be done offline, but there are, I mean, a lot of time demanding and resource demanding. And of course, they are relying a lot on our infrastructure, but also this highlights the need of a quality dimension associated to the products. The second example I would like to mention is related to another completely different application. And here I start by mentioning this catastrophic event that happened in June 2017 over a region in Portugal that caused several casualties and many injuries. And actually it was so catastrophic that it triggered, let's say, structural changes in the way the assistance of the fire events are now addressed by the European Commission. And this event probably happened because of a dry thunderstorm, and at the same time there was a very strong heat wave affecting the region. And it started a huge debate about how fire regimes are changing with climate and human activities. So the forest fires are an important part of the natural earth system dynamics, but there are studies that are saying somehow that they are becoming less predictable and more devastating. And let's say that the fire community would benefit from more data on fire observations to characterize temporal trends and identify also the impacts on population, on infrastructures, on ecosystems. However, the fire observations present a number of limitations. And so this is why there are quite in use fire danger models that are used. Here, the fire danger models do not predict where an ignition is likely to occur, but in practice they show the meteorological conditions that would cause the flames to spread out without control, conditional on an occurred ignition. And those conditions are named the fire weather. They depend on atmospheric variables, and this is an example, a specific example of a database that is available also in the Climate Data Store and produced for the Emergency Management Service. And this map shows the historical estimation of this fire weather index run on the ERA5 data, and that may be used as a proxy for flammability. The added value of running this product on those data is that, of course, it is possible to estimate statistics and trends. And this is the figures I would like to mention, that because fire weather index is not a directly observable measure, it is not possible to establish which deterministic model is closer to reality. So it is important to estimate an uncertainty and to put the long-term trends in the context of an uncertainties. This is the time series of the monthly spread of the fire weather index in the Portugal area, estimated from the ensemble of the ERA5. To conclude, we asked the same question to this community of users, and in practice, I would like just to highlight that there is a specific need of uncertainty estimation to interpret the temporal variations, but also the need of this longer time series back in time to establish connections, but also to, in general, this is relevant for any monitoring activities, trends, multi-decadal variability, extremes, or attribution studies. And finally, about which model component is mature and is necessary, and about the consistency, of course, a major difference is expected from this interactive or changing land use and land cover. So how are we going to address those needs? I leave Hans to describe the next two slides.
Hello, Chiara, thank you very much. So in a nutshell, ERA6 will make use of yet another additional 8 years of ECMWF research and development. So we get that from the research and development that is used, will be used in the next operational cycle that will start around beginning of 2024. So we get a lot of extra developments there, but of course we have to do a number of extra developments that make ERA6 also working back in time. So thinking about involving background covariance matrices, assessing, working on the systematic model bias to counteract on that. So Patrick will talk about that tomorrow, I think. Then, of course, we can run a higher resolution because we have an enhanced computer power and storage technologies also to archive more data. We will make more use of more and better observations, which are both reprocessed and rescued from satellite and in situ. And that we do together with our C3S contractors. So Bill will give a presentation on that tomorrow. And then last but not least, we make use of the invaluable feedback from our C3S reanalysis user community. So we have now nearly, I think we're about 100 short, about nearly 80,000 registered users on the CDS. And they provide a lot of feedback. We get a lot of questions and they have a lot of good and bad. They show us all the problems, and which is very good for us because we learn from that, and also our NWP learns from that because they review, because so many eyes on the reanalysis that they discover all kinds of things that we otherwise wouldn't have found. But they give also a lot of requirements, and those we try to feed into ERA 6. So ERA 6 will have an improved realism, so high resolution, 18 compared to 31. We try to do that also for the ocean waves, because in ERA 5 the ocean waves are a little bit lower resolution than 31. Then besides that, we also do regional downscaling via, for instance, the C3S regional reanalysis, and Anka will give a presentation on that tomorrow. And also we have this dedicated ERA 5 land, and we also have dedicated ERA 6 land products. Then we'll go towards coupling. Well, we start at the ocean. Either we do it a two-way or one-way from Ocean 6. Ocean 6 is a dedicated ocean reanalysis, which will start at the end of this year. Then improve forcing fields like aerosols, greenhouse gases, and potentially also a time-varying vegetation. Then we need to improve on the systematic model bias. And of course, that will lead to a better mean state and better long-term trends. And we get that via two developments. First of all, via a better model, but that's what we cannot solve. Of course, we need to patch it up, and we have reconstraint 45 for that, which Patrick will talk about tomorrow. The next slide, maybe. So we also want to enhance the uncertainty estimate. So again, we will look on the user feedback and also the user uptake, because what actually do they need? Because the moment we make available all the 10 members, we can ask ourselves, do users really want the 10 members? Maybe the standard deviation alone is enough. We have to investigate that. Then we want to improve the tuning of the error of the day. So really the uncertainty of ERA 5 at the moment provides the uncertainty of the error of the day. It doesn't provide an estimate for the mean state. So what is the uncertainty estimate of the 100 hectopascal temperature for a whole year over the whole globe? So we don't have an estimate for that. And we want to go towards that direction for ERA 6 as well. Next slide, next, please. Yes.
Can you please conclude soon? Can you conclude soon?
Yeah. Then the last point is also very important. We want to go towards more tailored products because the volume, it gets bigger and bigger. So for ERA 5 have about 10 petabytes, for ERA 6 maybe much more. So if you look at, for instance, the wind industry, they are interested, they were very happy with 100 meter winds. But I think they really want to have more layers in the boundary layer. And so we can do that by adding also height levels, which we don't have in ERA 5. So there you get wind, the temperature, and humidity at a number of levels pre-calculated. We'll have additional parameters. And of course, because of volumes will grow dramatically, that even if you have everything in the cloud, you still have to process a lot of data, and you want to pre-compute as much as possible. And again, based on user requirements, we will do that. And we were thinking about enhancing monthly products, so not only the means, but maybe also the standard deviation, the min and the max, and daily products, etc. Okay, Chiara.
Yeah, that's finished. I just will leave you with advertising this special issue of meteorological applications. Thank you.
Wonderful. Well, thank you very much, Chiara and Hans, for this very impressive talk on what might turn out to be services. If you don't mind, we'll go on to the next speakers because we're a bit over time. But please do stay online, because after the next speaker, we'll have another 20 minutes time for discussion. So please do stay by. So our next speaker is Mike Jacox from NOAA and PSL. And he will present on support of fisheries and ecosystem modeling.
Thanks very much. Start this up. Do you see that in full screen?
Yep. Okay,
excellent. Well, thanks very much for having me. I'm going to hopefully change gears a little bit in a couple ways. One, to draw our attention to the ocean, and the other to give some perspective, I would say a much less technical and sort of high-level perspective from outside the reanalysis community on some of the uses of reanalyses, how they're being incorporated in marine ecosystem and fisheries science. So I work between the Physical Sciences Lab there in Boulder and the Southwest Fisheries Science Center out in Monterey. So I'm really find myself at this interface of folks like you there producing valuable climate products, and then ecologists and others using them and trying to do that translation step. So I'll try to shed some light from that perspective. But the first thing I'll say is just that in the 5 years or so that I've been with NOAA, I've seen a huge increase in the use of reanalyses in marine science and in fisheries applications, which is really heartening and exciting for me, having come from working with them during my PhD. And so I'll walk through some examples of that work. But just to set the stage on the West Coast, where most of the work I've done is, there's two ocean reanalyses that have really gotten a lot of uptake. So one is produced by UC Santa Cruz, and this is a regional ocean reanalysis. There's actually a couple different flavors of it. And the other is the GLORIES global reanalysis. And there's various reasons why these two have gotten traction that I'm happy to get into, but obviously there's lots of details about these reanalyses and how they're run. But the information I put in the table here is like the level of information that a lot of these fisheries users are really interested in. So things like the resolution, things like the historical availability, and near real-time availability are really important. So a lot of what I'll show is based on these two reanalyses, but others have certainly been used. And then atmospheric reanalyses have been used a lot to force regional models and things like that are then subsequently used in marine applications. All right, so stepping through some of the ways these are used. So here's one example. This is from that regional ocean reanalyses of the West Coast. When we had the really strong El Nino in 2015-16, that was occurring on the backdrop of this marine heat wave, the blob that had started prior to that. There was a lot of interest in understanding how this El Nino was going to impact the California current. There were thoughts that it would kind of break up the blob, that it would bring storms, or it could augment the blob with warming and things like that. And so we turned to these regional ocean reanalyses for the first look at what was actually happening. And not just to get the near real-time assessment, but also the historical context that was enabled by these long reanalyses going back to the early 80s. What was able to really show ways that the response to this El Nino was quite different from the other ones it was being compared to in 82, 83, and 97, 98 in terms of sort of the scale and structure of warming. Sort of similar example using that same model is this product of upwelling indices. So off the West Coast, coastal upwelling is a dominant driver of biological productivity, and the reason that the West Coast is home to really valuable fisheries and tourism that's based on whale watching and all this kind of stuff. And so the scientific community especially is really interested in being able to monitor upwelling in real time, and again, place it in the context of historical variability. So this is another place where these ocean reanalyses at reasonably high resolution have been really valuable to improve upon historical upwelling indices that were based just on sort of estimates from coarse resolution sea level pressure. Here we're able to incorporate the ocean dynamics and higher resolution representation of the winds as well. And then the last one on just sort of the physical side, this is some recent work led by Dylan Amaya at PSL there. where the motivation for this was actually looking at sea level forecasts, subseasonal sea level forecasts along the West Coast. And what Dylan found was that the forecast skill was dependent on the presence of coastal trapped waves propagating along the West Coast. So the presence of these waves would enhance predictability of coastal sea levels, which is not surprising since they're modulating the sea level along the coast. So there could be an index, like a real-time index of Kelvin wave activity that could then be used to provide some information on sort of the conditional forecast skill. The likelihood that your sea level forecast at any given time is likely to have higher or lower skill. And so this index was initially constructed using the sort of long historical record. But then Dylan also went in and sort of did a synthetic version of it using near real-time data, which obviously doesn't allow for the same kind of filtering that's used in a long historical run, but found that it could be recreated reasonably well. And that this is another value or another product of value for us on the marine side in the forecasting in this case. All right, so moving on to the more sort of ecosystem and fisheries. And the use of reanalyses here is really as ocean state estimates, as a substitute for observations. And so the example here is a case where you have a whole bunch of data. So in this case, you have data in the top left there, two of those panels with the sort of blue and green. Those are showing data from observers. So boats, there are people out on the fishing boats that are collecting data on what's caught. And then the other one is tracks. So these are tags that are on different animals. So you can track where they go. So in all of these cases, you have information on the location of some animal, but you don't have information on the environmental conditions associated with its location. So that's where we're using reanalyses to go and find the environmental conditions that these species are in and construct models of their preferred habitat. And so then once you have these models, then you can take just the environmental data and create predictions of where they're likely to be. And there's a whole host of management applications for that kind of information, if you can estimate where different species will be. But I think a key point here is when people build these models, you can look at the relative importance of different variables. And so I won't go through what all of these abbreviations are. Some are obvious and some are not, but this plot is showing basically the importance of different variables. And the two I've highlighted in blue there are the Brunfeis-Halla frequency and the isothermal layer depth, which is just a mixed layer depth based only on temperature. And the point being that in this model, this is for swordfish, they both come out as really important and they're not available just from satellite observations, right? Like SST or SSH might be. So the reanalysis is valuable not just in sort of the spatial coverage, but also in the vertical resolution of the water column. And there's a whole host of examples of reanalysis being used this way for all kinds of species, turtles and fish and whales and sea lions and anchovies and sardines. So this is a really sort of booming area of research. And then a last sort of ecological modeling application. This one is for estimating not just the distribution of species, but how their populations change over time. And this is really important in fisheries management for setting quotas, basically for setting guidelines on how many fish can be caught in a given year, and trying to inform that by how many fish are going to be coming into the fishery. So here there was sort of a literature review done of what people thought were the drivers of variability or survival or mortality of this ground fish called sablefish, which is a really economically valuable fish off the West Coast. And these were things like subsurface currents and temperature integrated over certain portions of the water column that, again, you can't get from observations. So we extracted time series associated with these different drivers from reanalyses and found a lot of promise in improving the estimates of population responses. So then moving from direct use of ocean reanalyses to atmospheric reanalyses and sort of global ocean reanalyses, there's a whole lot of regional ocean modeling work being done along US coastlines and other places, obviously, but that's then being leveraged in fisheries science. And so here we're using global reanalyses to force these models. And so this is just, you know, you can see the variables that are needed in terms of output from those models. But this is a place where that development is really benefiting us.
4 minutes.
And then I think this is the last sort of main topic in terms of uses, but is in regional forecasting. So this is an example of some regional forecasting we're doing off the West Coast, and here in this case we're doing dynamical downscaling of forecasts. And there's a couple places here where reanalyses are really important. So one is for forecast initialization. We found that it's beneficial to initialize from a near real-time analysis as opposed to just downscaling the global climate forecast fields into the regional domain. But also when you get into skill assessment, shown here for SST, there's lots of SST products one could use for skill assessment. But as I mentioned earlier, people are really interested in a lot of other variables. Things like the upper ocean stratification or the mixed layer depth or the bottom temperature, where we really don't have coverage in order to be able to do these forecast verifications from observations. And so we're falling onto reanalyses to do that. So with all of that, there's been, I would say, a lot of increased effort to do verification or evaluation of ocean reanalyses, you know, on the regional scale and sort of for specific applications. So just a couple of quick examples. This is for sea surface height anomaly or sea level anomaly along the West Coast, comparing the GLORIES reanalysis to a whole bunch of tide gauges. And this is part of Dylan's work that I showed earlier. And then here, some other ongoing work comparing both surface temperatures and bottom temperatures to in situ observations. And finding, you know, good correspondence, but also not surprisingly that when you get to bottom temperature and you're further away from the constraint of observations, that the correlations are lower. And so we really need to, you know, we're really trying to quantify what variables are reliable or how accurate they are in different places in order to see if they're appropriate for use in these ecological models. So I thought I would leave with this slide, which is hopefully informative to this group as just some guidance or some requests, maybe more appropriately, from the marine ecosystem side about some key things that we're thinking about. You know, an obvious one is just how good are the reanalyses. But then another thing that comes up a lot is discontinuities or inconsistencies, either between historical products or when you're trying to apply a model that you fit on a long historical run using a near real-time run, and whether the delayed time and the near real-time are consistent. On the near real-time, again, if fisheries management decisions are going to be based on these reanalyses, then obviously they need to be delivered reliably. And then I'll stop after saying the concerns, and you can just sort of see the desires. But I know there's been talk about dynamical consistency, and I would say that in the applications to this point, it has been less of a concern. It's more of a just the state estimate on any given day that has been of chief interest, but that there certainly are applications where it could potentially be more important. People are looking at heat budgets, for example, or if you want to drive more mechanistic models, then you could have issues with shocks in reanalyses. Thank you.
Great, thank you very much, Mike. We have time for a couple of questions. Any questions in the room? Oh, yep. Well, I can start with one if there's none. And you had already kind of alluded to it about you know, the validation of the reanalysis. I mean, and that there could be actually a fairly strong feedback loop, right? So if you see that there's some systematic errors in the physical reanalysis, right? So that will likely reflect in your inability to, you know, have a good performance on your ecosystem model. Is there a feedback loop that actually you could provide back to the reanalysis community to actually say, well, look, we have either on this certain day or in a persistent way errors that that you need to fix from the reanalysis community in order for us to have a better estimates?
Yeah, I think there's a ton of potential for that. I mean, we have a really strong feedback loop like that with the regional reanalysis, just because obviously those relationships are tighter. And that's often how they find out that things are going wrong in the near real-time system, is because they hear from us. But we've seen some of that on the other products too. We were looking at sea levels in Aura S5 and had some back and forth there where we learned more about how the satellite data are assimilated and downweighted next to the coast. And so I think there's huge value in that kind of communication.
Any other question? Yeah, Sergey.
Thank you, Mike. Do you see value in the reforecasts? Like reforecast database similar to what European Center was describing for atmosphere?
So so I'm trying to, maybe you can elaborate on reforecast in this sense. So we use reforecast a lot for forecast verification, like when we're doing skill assessments of our ocean forecasts. But what, I guess, can you be more specific about the products you have in mind?
So for atmospheric reanalysis, it's common to come with a accompanying set of reforecasts produced by the center. So maybe twice a week out to 30 days, something like that. But for ocean reanalysis, I think it's still pretty rare to come with a set of standard reforecasts.
Well,
that's you
yeah,
guys
so like so the sea level work I was describing, those were subseasonal, they're reforecasts. I mean, absolutely, the reforecasts are essential for any kind of forecast verification. So there we're using the, you know, ECMWF S2S reforecasts to do the skill assessment there. We do the same on the seasonal side with the global climate forecast from a number of different modeling centers. But I guess the timescales that we're looking at for forecasting are typically a little longer than I expect that the atmospheric community is often thinking about.
Okay, so I guess a different requirement will be actually having seasonal reforecast. If we're including oceans in coupled assimilation, we should start thinking about seasonal reforecasts rather than, you know, 2-week reforecasts that we're used to.
Well, I mean, yeah, that would be fantastic. We're trying to get at that in various ways. You know, we are using the available global reforecasts where we can, and then we're also, you know, downscaling those in some cases.
Thank you.
There's a question online. I think we'll take this and then maybe open it up to a broader discussion. So go ahead, Anka.
Thank you. I put my hand up originally to ask Mike a question, but I wanted to comment back to Sergey's remark there. For example, ECMWF does reforecasts for each timescale with exactly the configuration of the system used for the real-time forecast. It's not the reforecasts don't exist in some kind of abstract situation. They need to be done with the same model with which you create your forecast, because you do them to learn the properties of your real-time forecast and to apply the information you get this way for calibration. So I think the creation of reforecast has to be connected with a forecast, including initialization schedule and length of forecast and everything else. I wanted to ask Mike, though, about there's an evaluation technique, the use of several reanalyses and the comparison of the stories from the reality represented by different reanalyses, in particular in the ocean, where we know that there are big differences as soon as you go away from the observed quantities. I know that there are objections for people who run climate predictions and who want to either verify or indeed to initialize that the reanalyses are not good enough at depth and everything else. I just wonder if in the user space that you have come across, or the experience you have, this comparison of the reality represented by several reanalyses is done regularly, frequently, or does everybody just use their own favorite reanalysis and leaves it at that?
No, there's more and more of it happening. So we've certainly started doing that. We've just done this analysis of a few reanalyses off the West Coast, comparing them against a whole different bunch of types of in situ observations. But in general, I think there hasn't been that much regional evaluation of ocean reanalyses. Like that field, whether it's a single one or multiple, I think that's a relatively nascent field that is now everyone is really recognizing the importance of, because there's such a strong desire to use the reanalyses like their observations. But I think where it is being done, often multiple reanalyses are being compared.
Thank you.
Okay, that opens the floor for more general questions also to our previous speakers, if anyone has any questions. I could start with one. It seems like in all of the presentations that we had, resolution, high resolution seems to be a very important issue, to the extent that you know, even at least in global products, you might not achieve the desired resolution. So is there, what is the thoughts on you know, the need for basically just for specific user applications, right? You might think that you have a baseline, you know, global product, but then you can have targeted, you know, areas where you really sort of crank, you know, really resolve the heck out of the system at the level that you need, for example, for wind forecasts or for ecosystem forecasts in coastal regions. Is that sort of I mean, in some sense, it's already done, right, with the regional awareness, but it seems that even there, the resolution isn't large enough. So what is the thinking there? Anyone? Let's see. Let's start with maybe Chiara, or Hans, if you're still there, or
if you're still there, yeah, if you're not asleep. Yeah. Yeah, I'd say that, I mean, so first of all, from the point of view of those specific users and application, thinking of this high resolution, that seems to be very important. Of course, there are solutions that are working right now. For example, many users are finding their own high resolution via processes that are happening downstream of the reanalysis. So in this case, there are specific statistical or dynamical downscaling that run on the current reanalysis and permit the user to make their own estimate. But probably this is, let's say, maybe we could separate those categories of users in two, probably, or the users in two big categories. On the one side, those users that need to have a very accurate representation of the current climate, and somehow this goes in the direction of what was discussed before, the idea that, for example, if you have you can make the best use of observation as soon as they are available, for example, and this means that you are pushing or reducing the model biases, handling the model's errors, and this means that you are somehow pushing toward a reanalysis that very well represents your current climate, versus different categories of applications where your analysis instead are put in the context of the past climate. So in that case, this kind of consistency over time is is a crucial element. So you have this double role of the reanalysis, and if you follow one pathway or the other one, you are serving a certain typology of users, but not other ones, of course. But you can also learn, I think, from I mean, there are also strategies and possibilities probably to learn. So, for example, I think something that happened in the past related to the improvement of the reanalysis when the GPS observations were included, and you were yeah, the possibility to improve one component, in this case, the stratosphere. But then, of course, it is difficult to apply the same kind of reduction of the error back in time.
Maybe if I can comment as well, I think whatever resolution you come up with will never be enough. So the sky is the limit, as high as possible if you can get. See the NWP as well. So we go as high as we can. And of course, that will never be enough. And therefore, we also do European, in CPS, we have the European reanalysis as well, which is forced by the boundary, that gets the boundary conditions from ERA 5. And there you can get much higher resolutions. For instance, for the Arctic reanalysis, we have a resolution of 2.5 kilometers. It's pretty high already.
Okay, well, the compute is the limit, right? Not just the sky, but maybe that fits. Or well, anyone has a question? Please jump in with questions. Oh, actually, we have a question. Yeah. So
yeah, Rolf Reichler at NASA. Just adding on to the resolution thing. I mean, Hans brought up ERA 5 land, ERA 6 land. I thought that was part of the motivation for those post-processed land reanalyses was to higher resolution at 9 kilometers as opposed to a 1/4 degree, give or take, with ERA 5 is. And for the land surface, already in the reanalysis in our geosystem, the land tiles are higher resolution than the overlying atmosphere. So we could think about outputting higher resolution land fields. We don't do that normally, but there's stuff that can be done. It's already being done that may be worth thinking about for the next go around. Just adding that as a piece of information.
Yeah, Ron.
Ron Gilero, NASA. So there were a few slides, I guess it was Mike's talk, and they were all very good talks, by the way, asking what extent can the reanalysis be treated as observations? And I don't know if this is a semantics issue or something that we should really communicate better with users about, because reanalyses are not observations. And I don't, like I said, I don't know if that's semantics, but from our point of view, from the producer's point of view, they're not observations. They never will be. It's trying to be something different than that. So I don't know if that's something that, as an overarching issue, we need to communicate better about, or it's, like I said, or it's just a minor semantics issue.
Yeah, that's probably my fault on communicating what I'm saying. But I mean, in lieu of observations, can they be used as observations would be used, or what are the limits of that?
Yeah. So in other words, I guess the question is, to what extent can they be treated as truth? It's kind of what we're really.
Right. That's also true of observations when you phrase it that way. But yeah.
Exactly. Right.
Sergey, did you have a?
This is Sergey from NOAA. I have a question for Chiara. How do you guys draw the boundary from where Copernicus service provides products and the private industry starts picking them up and developing some user applications? Because you showed a couple of examples that seem so tailored to wind industry or solar industry that where does the private sector starts and the public sector stops?
Yeah, I mean, we have had several examples of private companies, or there exist several private companies, especially in the energy industry, that they make use of our products to build their downstream service and serve their own clients. And of course, our activities stay very close to the data, in the sense that what we have to ensure is that we have this robust, maintained chain. For example, the reanalysis product that is there, that is reliable, that is in near real time. And often what we go is we make a step toward closer to our users, for example, highlighting a quality information. The quality control information is something that different users want. But of course, we do not want to step on the different activities of the downstream sector and commercial applications. So we don't want to substitute at all what the downstream sector is doing with respect to our application. So our role is really to support as much as possible I mean, any kind of, whatever it is, public or private, it doesn't change much. Also, I think that we have created in the past specific use cases for which we paid different commercial entities to understand and to demonstrate which was, I mean, the information that they needed from our side, and to create a full data value chain from our products until their downstream element. But our role is really to support. It is not to substitute and to step on toes of those downstream applications. But I agree with you, it is not easy, the separation between the two, and especially it strongly depends probably on the sector and on the specific applications.
Thank you.
Any other question? Maybe still related to the resolution and the sort of the flood of data that is being generated. For example, we have ERA 6, the type of resolution that we have, and similar efforts in the US. What is the vision? Clearly the vision of downloading the data to do analysis is less and less feasible. Even if one wanted to do it, it's just not feasible anymore. Which means that in order to provide useful analysis on those data, you have to provide compute power close to where you store the data, right? So that comes back to this cloud issue. What is there? Is this infrastructure something that we need to worry about? That is this being developed side by side as the data are being produced? And related, maybe, if one wanted to query, let's say, 3 reanalysis, I want to compare the ERA 6 with the GMAO MERA 4, and then sort of the Japanese, whatever next generation product. They sit on different parts of the world. How would one, is this still something that's sort of that we can do today, or that for which an infrastructure is needed to do tomorrow?
Maybe I can add a quick comment on that based on the experience at C3S. That somehow, as you may know, at C3S, there are a lot of data that sit in our infrastructure, and the infrastructure includes a software, so a toolbox that permits as much as possible to operate on the data that stays on the infrastructure, so without any need to download. Of course, there are still limitations, and we are in the phase of expanding the toolbox. But I think interoperability of data was one of the key aspects behind the development of this toolbox infrastructure. But yes, there is a lot of need from that, and yeah.
If I may add, it is also important to pre-compute things that people need likely. So, for instance, the monthly means is a good example for that. So, because a month is a nice length of that people, typically climate scientists, are more likely interested in, less than the hourly. The hourly is really for other applications. But also the month, you have there's about 24 times 30 is 360 hours in a month, and 360 months is about 60 years. So 1 month sits exactly in the middle, the square root of the number of time steps you have. So you only, if you divide your data set in such a way that if you have n different time steps and you only have to download up to square root of n, then you're much more efficient. So just by the way you pre-compute the certain quantities, that also allows users to the need will be much less to do brute force calculations, even if it's in the cloud. Because even if it's cloud and even if all the data is together, at some point you still have to do the number crunching. So it's 2 parts. There is the moving the data from A to B, but it's also the number crunching, and that at some point will also become limiting.
Thank you. Is Katie, please? You want to come to the mic?
I guess given the size of the data sets, even if you're
your name,
how's that? Given the size of the data sets, even if you're logged into Copernicus, doing any kind of preliminary analysis is going to take forever. It's a lot of coding and so forth. So, well, not to toot my own horn, but getting tools that can look at differences that are, much quicker to compute, so scientists and so forth can look at the data in a way that's quick and easy, and then go into the harder computing with maybe higher resolution data might be the way to go. So just tools like we have like RIT, but also producing either atlases or collections of comparisons or other sorts of statistics, so that people don't have to go immediately and work on a petabyte of data just to do some preliminary analysis.
Okay. Yeah, maybe we'll come close to, well, I mean, any more question maybe from online? Any question? Okay. Well, thank you very much to all the presenters.
Never mind.
Oh,
Go
yes.
ahead. No, it seemed like Anka had a question, but maybe we can reserve it for the breakouts.
Okay. Okay.
Sorry.
Yeah, go ahead, Anka.
Go ahead. There's time for.
I was just going to make a comment because I'm not sure if we fully addressed Patrick's question originally, the one about how do you operate data that does not sit in the same place. I mean, one thing is to provide the compute next to the data, but if you want to compare the Japanese reanalysis with the one in Reading, it's not that easy. So I think we need to put the idea forward that the producers and providers of reanalysis data ought to provide technology to allow this kind of interoperability. At C3S, we've done this with the Earth System Grid Federation, who host the climate projection. So we do have an interface and web processing services that allow us to simplify the data to do some pre-computing next to the climate projection data and comparing it to only bring small amounts. So in other words, it's something that everybody needs to sign up to if we want to do this kind of thing. It wasn't that important.
Great. Thank you, Anka. Okay, well, that concludes this session. And thanks again to all of the speakers.